In this video, we are going to derive the formula for mutual inductance. It is usually represented in terms of capital M, in terms of coefficient of coupling. So, coefficient of coupling is nothing but K. Okay, as in self-inductance represent as L. You can consider this as a circuit. Okay. So, it is a coupled circuit, and M represent mutual inductance. I1 and I2 represent the current flowing through the coil, and L1 is a current flowing through this one. L1 is a self-inductance, L2 is a self-inductance of the second coil. Okay, and V1 is a voltage. Okay, V1 and V2 are the voltage. So, in order to derive the formula for the coefficient coupling, first let me take the case 1 where I1 and I2 is equal to 0. Okay, so if I1 and I2 is equal to 0, there is no energy stored in the coil, right? So energy stored in the coil, in both coil. Okay, so that is W, okay, is equal to 0. So let me consider the second case. Okay, that is case 2. So what is the case is I1 is increasing from 0 to I1. Okay, and I2 is equal to 0. Okay, so if I2 is equal to 0 means there is no power or energy that is produced in this second coil. Okay, and I1 is 0. I1 is changing means meaning there is a possibility of producing the voltage at the so if I1 is changing means I can write what is power? Power is equal to, okay, V1 into I1. Okay, so this I1 I can write it as V1 into V1 to I1 I can write it as V1 I1 I can write it as I1 V1 I can write it as L1 into dI1 divided by dt. Okay, since I1 is equal to L dI, V1 is equal to L1 dI1 divided by dt. Okay, so this I can write as P of t dt is equal to I1 L1 dI1. Okay, so if I integrate this value, integration of P of t into dt, that is nothing but your energy. Okay, that is equal to L1 integration of this is from 0 to t. Okay, and this is from 0 to I1. Since I1 is changing from 0 to I1, okay, dt, dx, right? So I can write the energy is equal to L1. If I integrate this one, I will get I1 square divided by 2, 0 to I1. Okay, so if I substitute, I will get L1 I1 square divided by 2. Okay, this is your energy. Okay, that is W1. Whereas W2 is equal to 0, right? So the total energy is here is L1 in L1 I1 square divided by 2. Okay, so next let me go for the case 3. What is the case? I1 is equal to I1. It is maintaining the same current. Okay, and I2 is increasing from 0 to I2. Okay, So due to the change in the current of I2, I will get voltage of V1. I can write it as V1 is equal to M12, okay, M12 into di2 divided by dt. This is a voltage at the primary side, okay. So I can write P2, so P2 of t, okay. P2 of t, I can write it as V1 into I1 plus V2 into I2, right? So in this instead of V1, I can substitute this one, I1 M12 di2 divided by dt, okay. And so instead of V2, I can write it as L L2 di2 divided by dt. Okay, so this is your P2 of t. Okay, so if I solve this one, I will get W2 of t. W2 of t is nothing but P2 of t of dt. It is changing from 0 to t. And this I can write it as M12 of 0 to I2, right? 0 to I2, I1 and di2 plus L2 into 0 to I2, I2 di2. Okay. So M12. So instead of this I1, I can write it as, because here in this case I1 is equal, small I1 is equal to capital I1. So I can write I1. Okay. So this is nothing but I2 0 to I2 plus L2. This integration is I2 of I2 square divided by 2, 0 to I2. So I can write omega 2 of omega 2. Omega 2 is equal to M12 I1 I2 plus L2 I2 square divided by 2. Okay. So now I can write the total energy stored in the coil. In the coils when both I1 and I2 have reached the constant value. Yes, sir. Can. So this is omega 2 and this is omega 1, right? So this is your first equation. And this is your second equation. So I can write total energy. Omega is equal to omega 1 plus omega 2. Where omega 1 is L1 I1 square divided by 2 plus omega 2 is M12 I1 I2 plus L2 I2 square divided by 2. Okay. So next we are going to do it in the reverse order. Okay. What is the reverse order? What is the reverse order means? So case 1 is same. Okay. If I1 and I2 is equal to 0, the energy stored in the coil is 0. Okay. So what I am going to do is for the case 2, I2 is changing from 0 to I2. Okay. So I2 is changing from 0 to I2 and I1 is equal to 0. So if that is the case, what will happen? I will get omega 2. Okay. So for the case 1, there is no energy, right? For case 1, omega is 0, which means I1 and I2 is equal to 0. For the case 2, I'm going to change this I2. Okay, I2 is increasing from 0 to I2 and I1 value is 0. So that is the case. You can write omega 2. Omega 2 is equal to L2 I2 square divided by 2. Okay, so this is your third equation. Okay. So what is case 3? Case 3 is I'm going to maintain this I2 value is equal to I1. Sorry, I2 and I1 it is increasing from 0 to I1, capital I1. So if that is the case, you know the value of omega 1, right? What is omega 1? Omega 1 becomes L1 I1 square divided by 2 plus M21, right? M21 I1 I2 plus L2 I2 square divided by 2. Okay. So this is your fourth equation. So if I add this omega 1 and omega 2, I will get L1 I1 square divided by 2 plus L2 I2 square divided by 2 plus M21 and I1 I2. Okay. So this is your sixth equation and this is your seventh equation. Okay. So if we compare this fifth and sixth equation, we will come to a conclusion that M1, 2 and the M2, 1, I can write it as that is equal to M. Okay. So I can write omega is equal to L1 I1 square divided by 2 plus L2 I2 square divided by 2 plus M I1 I2. So this is your final equation. Okay. So if you see the diagram, okay, if you see the diagram, here both the coil are entering. Okay, if both the coil are entering, or if the both the if the both the current are entering to this dot, or the both the current are leaving this dot, M is positive. Okay, if it is in the opposite direction means I can write that is if one current is leaving, okay, and another current is another current, that is I1 is consider I1 is leaving and I2 is entering the dot, okay, and vice versa, M is negative. Okay, so if that is the case, I can write omega is equal to L1 I1 2 I1 square divided by 2, L2 I2 square divided by 2 minus M into I1 I2. Okay. So both the equations are same. Okay. So I can write omega is equal to L1 I1 square by 2 plus L2 I2 square by 2 plus or minus M I1 I2. Okay. So you know that whatever the case, the energy should not be zero. So if the energy should not be zero, means considering the eighth one, okay, let us take this eighth equation, and I'm going to write L1 I1 squared divided by 2 plus L2 I2 squared divided by 2 minus M I1 I2. That should not be, it can be 0, but it should not be negative. Okay. Energy maybe it will go to 0, but it should not go to negative, right? So this is from 8th equation, right? So in this, I'm going to add and subtract I1 I2 root of L1 L2. Okay. So I can write L1 I1 square by 2 plus L2 I2 square plus
And sweetly, but if I start about the other,
I1 I2 root of L1 L2
and but it's in it.
so I'll find out capitally. Okay. Minus I1 I2 root of L1 L2 minus M I1 I2 greater than or equal to 0. Okay. So this I can write it as I1 root of L1 minus I2 root of L2. Okay, the whole square. If I do it, I will get I1 square L1 plus L2 square L2 I2 square. So you have to give 2. Okay. Minus 2 into I2 I1 root of L1 and L2. Okay. So these 3 terms will come here. Then plus I1 I2 root of L1 L2 minus M into I1 I2. That is greater than or equal to 0. Okay. So you can see this this square term, right? The square term is always positive, right? Always positive. Okay. So if it is always positive, we have to consider only this term. This term should not be less than or it should be greater than or equal to 0. So I can write I1 I2 root of L1 L2 minus M I1 I2 should be greater than or equal to 0. So if that is the case, I1 I2 root of L1 L2 greater than or equal to M into I1 I2. So these two terms get cancelled out. So I can write MS less than or equal to root of L1 L2. Okay. So M should not be greater than geometric mean of that is mutual inductance should not be greater than geometric self-inductance of the coil. Okay. So I can write this as a M is equal to K into root of L1 L2. Okay, where K is equal to M divided by root of L1 L2. Okay, so this so this is the maximum limit of this mutual inductance. So this K represent coefficient of coupling. Okay, so this K value ranges from 0 to 1, and whereas M value ranges from 0 to L1 or L2. Okay, so this K, okay, that is the coefficient of coupling. I can write as 512 divided by 5.1, that is equal to 512 divided by 5.11 plus 5.12. So if K value is 1 means it is perfectly coupled. Okay. If it is 0, if it is less than 0.5 means it is loosely coupled. And if it is greater than 0.5 means it is tightly coupled.